All right, so I'll pick up where I left off on last time when Garrett actually stopped by and Clee invited me to give a talk on the QSN, even though it was very early in my understanding of the QSN, but I tried my best. So what I'm going to go over now is how physics can be extracted from E8 and connecting to the standard model as well. So I have Garrett's Elementary Particle Explorer up here. And the labelings I'm not going to use fully because Garrett has his own labelings and it ends up being a little different for my use here. So we'll actually open this up. So here we see all the root vectors for E8 flattened down on a plane. And it looks very messy and intricate, or it could look very lovely if you look at them as flowers, right? So we will actually go to a slightly more symmetric view of these. So we have a theory here.
Yeah, this view is interesting because you have the two 600 cells.
That's true. Yeah, it's interesting in some respects. So I switched to the E6 Coxeter. So it's actually, we're going to look at the E6 structure here. So let's try that out here.
Mike,
Yeah.
so that's the same projection angle, but with everything other than the E6 subspace removed?
Yeah, it's just being rotated so the
But it's the same.
the E6, yeah. So the E6.
But it looked like it was the
It's
same
obvious.
rotation angle as the previous full set, and then you just take out all subspaces other than E6, and it gives you this. Is that, or is that not correct?
No, you don't remove anything. You just rotate it so the E6 part is manifest. So what I'm doing is I'm adjusting that. So that's the E6 Coxeter plane. So the E6 is manifest there. And then I'm going to shrink this down. And we have this very interesting special projection, which has come up in other talks. This was Piero had actually looked at a star structure for this. So you can imagine some lines here and some lines there. So each of these has a 27 here. So there's 27 on each. And right in the middle, that's actually the E6. So the E6 is the 78, 6 times 27. We have these outer 6 here, which is an SU3 or an A2. And we have the 2 axes here. So those all add up to 248.
So in other words, those 27 are just the superposition under projection of
Yes.
27 root vectors.
Yes. So what ends up happening is these, instead of thinking about them as just 27 roots overlaid on each other, there's actually an algebraic structure within those, which is the same algebra found by von Neumann, Jordan, and Wigner back in 1934. So that's the exceptional Jordan algebra here. So it's nice, it has its own little algebraic structure within it. So what I'm going to do is just blow it up a bit so we can kind of peer inside. So you see what happened there. So these are labeled by Garrett as X bosons because they're a bit mysterious, right? X unknown. And you see here, there are some roots that are right there on those edges. Okay, so there are 8 in each. So we have 24, 25, 26, 27. So now we can actually peer inside the structure there. So this...
Can you move the mouse to that side?
Sure, yeah. Let's go here. Probably place it there. Okay. And you saw that as we did that the E6 actually popped open too, and it looks like a little smaller star shape, which it does have, but it's tilted a bit by an angle. So Okay, so we'll go back to the algebra now. So what does this look like algebraically? So the 27, we can call that the exceptional Jordan algebra. Yeah, I'm going to get to it right there. Okay. J3O. Okay, so they're going to be 3x3 matrices over the octonions. Okay, so the octonions, if we recall, the division algebras. Okay, so these are algebras such that this property, A times B equals 0, implies that A is 0, right? Or B is 0. This is what we expect. This is what we've been accustomed to and to expect in algebra. So, or they're both 0, right? Or both. So that property is satisfied by the one-dimensional division algebra, which is a set of real numbers. We also have the set of complex numbers in 2 dimensions. We have the quaternions in 4 dimensions, and we have the octonions in 8. So dimension 1, 2, 4, and 8. So these are finite dimensional division algebras, and these are the only ones that exist. So it's a funny story. Yeah.
Cole Fury in the video that you had me watch, which
Yes.
I found very elegant, and she's a great teacher.
Mm-hmm.
So of course there she was referencing them as number systems. I understand how they're algebras and number systems, but so can you say something that illuminates, I mean, essentially I kind of relate the 4 number systems to spaces, spatial spaces. You know, in the easiest case is to see the real, plane, the imaginary plane. And is it correct for me to then just take that same concept to the quaternions and imagine a 4-dimensional space, and with the octonions, it's a number system arrayed, and because they're arrayed,
there's a space.
And because they're arrayed like that, you have these natural kind of cross operations that are algebraic, where you can sort of combine numbers in different ways, and then that defines an algebra on these dimensional number systems. Okay.
Yeah, you can give them a geometric interpretation because you can express them as n tuples, right? So this would be an 8 tuple. This would be like a 4 tuple. But then you can also write a quaternion, for instance, as 1 plus I plus j k, where any of these behave just like the imaginary unit. So,
and then and that's where guys like Tony Smith, who prefer to work their algebra in geometric senses using Clifford rotors and geometric operators, just sort of do the whole thing in a geometric kind of lens.
Yeah, so if you go to the geometric picture, you can think of these as unit vectors, right? These different directions here. The ijk, and for this, for the largest case, the octonions, I'll just go ahead and write them as basis elements in terms of E. So we have E1, E2, this is just more general notation. E3, E4, E5, E6, and E7. Okay. So there's a certain multiplication table for these. So the ijk is pretty simple. Right, we can just define an orientation here on this graph, and we can say, okay, I times j is k, right? J times k is I, we can go backwards against the flow. I times k is negative j. So by this orientation, we can get these properties essentially. So.
And that's why it's called a vector algebra, because you have a notion of vectors in your.
There's a certain at this you can actually I mean historically, the concept of a vector, three-dimensional vector, came from ignoring the real part. You see the ij and k, and if you look in a lot of textbooks that are teaching vector analysis, you have an ij and k there, and students are wondering where do those come from, and maybe that's just convenient notation. No, that was the original notation from Hamilton, because he was trying to create a division algebra in 3 dimensions and wasn't able to do it, so he went up to 4. He got very excited and he scribed on the bridge.
So he's the inventor of the quaternions?
Yeah, that's why it's H for Hamilton.
Hamilton.
Yeah.
And also the ij equals k, as Clee said, it's a vector algebra because this is the vector product in 3 dimensions.
Yeah, you actually relate it back to vectors. And it's deeply, I mean, vectors came from this.
Yeah.
And many of the vector properties follow from this. But when you learn about vectors these days, this isn't seen. You don't see it as hyper complex numbers. So, but in this case, when we're doing E8 physics, we have to actually get down and dirty. So the multiplication graph for this is the Fano can be written by drawing the Fano plane out. So I'll go ahead and draw it over here. So let's go with an E6 here, E4, E3. I'm just following John Baez's notation, by the way. So you can label this differently, but for the purposes of the talk, I'll just go ahead and roll with this. And we have the E7 right in the middle. Okay.
Yes, this is the wrong table. So this is the original table from Dixon, but this is not the table with the XOR, because 6 XOR 4 is not equal to 3.
Yeah, let me shift this over a bit. Make it look a little prettier. Right. Yeah, this is the one that you'll find by Googling.
Not on Wikipedia. But historically, this is the first who was used, which is bad.
So you see there's a sense of flow around the edges. So it's a generalization of that there.
What about the E7 to E2?
This is not the best.
No, this is the worst. But this is the first who was used.
Yeah. There's a whole class of symmetries of this, or relabelings that you can even execute. So.
There's also between E4 and E1.
Yeah, we have this, and then we're going up here. Yeah.
So E6 times E1 equals E5?
Yeah.
E4.
So you see, we have properties of this form. We have quaternionic circuits in here, where the E6 times the E1 is E5 here, at least by this this labeling. Okay, and you can go against the grain or the flow, and you can say E1 times E6. Right, if we go against it, we're going to pop up here, but we go against the grain, so it's going to pick up a negative sign.
So Mike, it seems to me like this relates to rotations. You know, if you imagine rotating a hyper Rubik's Cube or any, hyper shape, as you rotate it, it seems like you can get these values similar to this form where E6 times E1 becomes E5. Like it seems like it's all related to essentially projective geometry, so rotations under projective action.
Yeah, you're right. This is actually a projective geometry as well. Just
Yeah.
even the plane, the phonoplane.
Cool.
So it's deeply related to all those concepts in it. And
So
it's
that
going to come up.
algebraically, you have a system and we can add vectors together. We know how to do that. But
Yeah.
to multiply them together,
Yeah.
it's like, what's this times that?
Right.
So in a complex plane, to have like one vector multiplied by another, it rotates it
Right,
by that
right,
much. And
right.
same thing in quaternions, octonions. You're
Right.
just having a lot of rotations
Right.
when you multiply.
Right.
Yeah, you can do it algebraically, or also an isomorphic way would be to use matrices. So you have 4 components,
So
or you can.
am I
use
going
quaternions.
too far then to then deduce the next statement, which is that these algebras are deeply related, therefore, to projective geometry?
Mm-hmm. Yeah. And they actually give you a very special projective geometry that corresponds to the 27 here. It's maximal over the octonions. You can't define a larger projective geometry over it. So the corresponding projective geometry for this Jordan algebra that we can see as roots of V8 is called the Cayley plane, or the octonionic projective plane. Or Cayley. Wufang plane. That's another way that you'll see it pop up, and it's denoted OP2.
So this is really in line with my thinking that these AB equal P operators being isomorphic to projection operators relative that are isomorphic to a D4 subspace acting multiplicatively as a projective rotation with the E8 root vectors. Like that seems to be
Yeah, they're
fitting
related.
right into our
Yeah, I'll even probe down into there. So we're going to get into the guts of this.
okay.
So we can even go deeper in here. I was just giving an overview, connecting it with E8, so we can see we're kind of just peering into it. So what we did is we got E8, we put it in the E6 Coxeter projection, and then I shrank, right? I shrank the nose. I shrank I made these root vectors coincident to a point, and then I fleshed it out so we can actually start seeing the structure. So this is very nice because, as you see, Garrett has labelings here, which he assigned quarks here, you see. But this algebra is a little picky about what it wants to do at any given time. So to assign quarks to all of these 8 roots isn't possible at a given time. You have to, some of them like to be bosons, while the other ones like to be fermions. So which one is which? It just depends on transformations.
On the rotation.
Yeah, there's transformations of this plane.
Which is exactly the quasi-crystal principle. You can't have every all these identical vertexes in the integer lattice associated with the integer algebra. Then all those have to get converted in different vertex configurations in your projective space. So they can't all be the same.
No, not at a given time.
It's conserved as well.
There's the notion of a fixed point for the transformation. So given the fixed point, that'll determine who's who, what kind of labelings we give. You can say these are stabilizers.
Yeah.
Stabilizers, and the stabilizers do appear within the reflection groups of the E8 root vectors. So you're right, this is all tied together. Okay, so we can consider, so we have an idea of how to use these imaginary units and that they have a multiplication. So we can relate it to Colfuri's model and to other models, let's say Sultan Kato, even Fizigursi, who's one of the fathers of using exceptional structures within physics. So these are very provocative, and if we think of the symmetry group or the symmetry algebra of this here, of the octonions, the largest division algebra, we start recovering exceptional structures already. So if you recall the exceptional Lie, let's look at the Lie group level. We have a G2, F4, E6, E7, and E8. And that's it. So we've seen discussions, maybe even online. There was Eric Weinstein actually discussed these exceptional structures being kind of oddballs within mathematics, right? He called E8 the monolith, right? The monolith. It's like Stanley Kubrick's film 2001, where this monolith is there and nobody knows why it's there, but it's so beautiful and perfect and has such power and mystery. So that seems to be the largest of this family.
And the symmetry of the monolith is the Gaussian polytope, right? So that's kind of like a 8-dimensional 24 cell or 8-dimensional cube octahedron.
Right. So there's also the geometric way to view the roots of this object, which is the Gaussian polytope. You're right. So there's a geometric and algebraic way to view these. So G2 ends up being the symmetry of the octonions. So we can write symmetry group, automorphism.
What does the G stand for?
Group. The G2?
The G, what does it stand for? Gaussian?
No.
Just A, B, C, D, E, F, G.
It's just,
the
name that it
number,
picked up.
Yeah, the letter, okay.
Right, yeah. Yeah, if you remember the A series, the B,
yes.
so it fits in there.
Okay.
But it's related to the A2. It actually contains the A2.
Okay.
Yeah, so it's very nice.
So you could build G2 with some quantity of rotated A2s.
It's like a
It's
2A2?
It's A2 with
two offset A2s.
it's there's some extra roots.
Okay.
Yeah, it's an augmented A2, which is going to be important for trying to recover physics. So we'll get to that. So automorphism, G2. And we can ask, how does F4, E6, E7, and E8, how do these come up? What are these symmetry groups of? Okay, well, it turns out F4, we can relate it to this object, the 27. So it's actually the automorphism group of this algebra right here. So we're getting a little more bang for our buck. It's all giving you these objects for free. So J3O. So we have the F4 there.
So Mike, I have a question.
Yeah.
So, a lattice doesn't necessarily, as a word, indicate that there are connections on it. In other words, it doesn't indicate. It doesn't say whether it is or is not a crystal with edges drawn upon the lattice. But when you're dealing with root vector algebras and their associated root vector lattices, in that case, the lattices are crystals. That is, they are point sets connected. And so when you think about A2, the A2 lattice, or drawing upon the A2 point space, then you've got your connections. But if you were to offset two copies of A2 such that, like in your diagram, you get a connection. You get a point in the middle. You don't necessarily get connections. You don't have to have connections. In other words, imagine you had two copies of A2 and you offset it such that the vertex of one A2 is where you have E7 in your diagram.
Yeah.
And so there would be no connections between that vertex necessarily and E1 and E3. Necessarily, I have to visualize it. But anyway, the question is, that's the setup. And the question is, so it seems that these root vector algebras deeply relate to connections. And where you have two algebras like let's take A4 and D4. They're not the same. In 3D, they're the same, A3 and D3, but in 4D, they're not. And it seems that the sameness relates to the connections, or can maybe perhaps relate to the connections.
Like a directed graph, you mean?
Right.
Yeah. With edges that have direction.
Like where you have more connections. Like,
right.
Imagine you take a cubic lattice checkerboard, you start drawing diagonals. Well, that would be the same point space, but connected differently.
Right. Yeah. So the QSN inherits the structure. It has actually directed edges. Yeah. And these would be given by the root vectors. So the root vectors are, you can think of them obeying algebraic relations. So we can ask, I have another talk coming up that will further explore that. The more the graph theory, the capacity of nodes, because we can start using this structure to describe this network. Because it is a network, if you use E8 to acquire the QSN, for instance, and that is a network, and we can ask, what kind of network is it? And we can ask if it's even solvable. We can actually have a solvable network. So it turns out it's very nice. That'll be for the next talk, but there is actually the structure of a matroid here. So matroid is it's a graph theoretical concept coming up from combinatorial mathematics that enables us to study the 600 cell. So if we peer into that graph theoretical picture of the 600 cell, it gives us a different way to study the network. So that's going to be for a different talk. But for right now, it's good intuition. It's good to review these at least before we go into those other concepts where we start actually having to solve the network. Right. Yeah. And we can imagine what that would mean to even solve it. But it's very, very much rooted in computer science.
Yeah. Can you just draw a hexagon really fast?
Sure. Yeah. So we have.
Now draw a center point and then connect it to each of the vertices.
Yeah.
Let me see.
And
All of them.
All of them?
Go ahead and leave just those. So what
No,
just leave those. All right. So okay. So what I wanted to point out is that relative to the projection plane, you have some edges. Like so you have some edges that are rotated in one direction relative to the projection plane, and others that are rotated in the opposite direction, the same angle but the opposite, like negative. And it seems that with quasicrystals, like take the Penrose tiling or the QSN, when you look at the graph itself, if you don't label the connections at all, okay, you can get two connections of the same length magnitude, but you wouldn't know unless you label them what the angle of of that edge was. And there aren't a lot of angles. There's a small set of angles. So it seems like when you think about just generalizing the notion of directional connected graphs, right? And this idea of root vector algebras where you've got a direction on your vector or on your one simplex, it seems like we're going to have to decide whether or not we need to do it for some physical reason or not. But it does seem deep to me that in the higher dimensional space, I can have one angle rotated relative to my hypervector and the other one completely the opposite. And in my projective space, I will have no information unless I label it
Right.
of what that those two opposite sign values are of the same integer,
Yeah.
the same value.
So going back, we can return back to the discussion of the Hope vibration that corresponds to the QSN. So I'll just draw it up so we can recall the deeper structure of the 600 cells. So discretized Hope vibration. So we map from the 7 sphere, S7, over to the 4 sphere with S3 fibers. And of course, all these are discretized. So we can, of course, drawing just a picture here. Of course, it's not accurate. And we have the 240 points being mapped over here. Kind of visualize an equator there. And we have our 24 cells here. So this is a very helpful picture as well. And this exists in 5 dimensions. So we'll project down from a privileged point. Usually it's, this one's very nice. Right, and we project down. And we get 1/600 cell, and we have another one inside it there. So it's just one way to view it. So this is from the last talk here, but we see the star of the show here are the fibers. So the 24 cell.
I don't understand what you did. So you went from S7 to S3 to S4?
Oh no, it's S4.
All right,
but
so
then the fiber was the S3.
Fine, but
Yeah,
how do you get 600 cells
It's
from
from the-
S4?
It's from we're projecting in 5 dimensions.
Each little circle you drew on the 4 sphere is a 3 sphere. Each
Yeah,
that
these
little
are all-
loop there. And that's a
these are all
24
discretized.
cell.
It must be because these 24 cells that live in 4D, they can be composited into the 600 cell, right? If
Yeah,
you have
yeah,
5
so there's-
24
Yeah.
cells.
Yeah, so
That's
we're
fine.
524.
we're breaking up into like equators.
Got it.
Yeah, we have our hemisphere. We have the equator. Sorry,
Got it.
equator. Hemisphere 1, hemisphere 2. It's just a way to.
Oh.
So it's just a nice way. This is the way that it was shown to Garrett last time. So he kind of liked it.
So you're orienting 24 cells on an N sphere, which is very different than the 24 cells that would live in something like the D4 lattice. I mean
These-
you have 24 cells in the D4 lattice, but when you do it on an S4 sphere, it's in a 5-dimensional space. So you can kind
That's
of
the
have
base.
So
yeah,
this is
that's S4 is the base.
Uh-huh.
So you project
The
it
D4.
down them now.
You're right.
So is that a stereographic projection down to
Yeah.
R4? The North Pole, yeah.
That's cool because I thought you could only get the 600 cells by projection from the Gaussian polytope, but this by relating it to a 4
It is the Gaussian
Yeah, the
polytope.
Gaussian polytope's here. We look at it as the discretized
Yeah.
7. Yeah, so it's actually here, and we are mapping the Gaussian polytope to this structure.
Uh-huh.
So these are what you call 5 compounds of the
Okay.
24 cells.
Okay,
But we grouped them up into hemispheres.
got it.
So it's pretty slick. So we also know the 24 cell as related to D4 or the SO8. The SO8 root vectors. So this is actually, so the 24 cells, otherwise known as SO8 root vectors, become the star of the show here when we're relating it to physics. So that's what's floating around in the 600 cell. So we can think of, right, the 600 cell as a 5 compound of these 24 cells. So it's not surprising that the physics should pop up from that, right? Okay, so we have the picture there. we have, so we're laid it back here, so we have a notion of these structures here, so I'll have to probe a little deeper now. So we'll go back into matrices now, so this isn't...
Just on general comment.
Yes.
This picture of the H unification is like you start like electrodynamics. So you look at each point of space-time.
Mm-hmm.
You have a U1's gauge field.
Yeah.
Then you go to unification, you see if it's have more energy. So
right.
you can have a U1 cross SU2.
Yes.
And then SU3
yes.
in the same point of space.
Yeah. Yeah. So
and then you can go to the H. So if you close to the Planck scale,
right.
you have all the fields.
Unified.
U1, SU2, SU3,
right.
SU5, E6,
uh-huh.
and finally E8 and in just one point of space.
So you go to very high energies, right? Yeah, that's what.
So I was thinking.
That's what the dream is.
Yeah. So, but you need the space-time to define the fiber bundle structure.
Yes, you need a base.
Yeah.
You need a base, so.
Like in that picture, you need the base.
Right.
So I was thinking, when you set quantum gravity in the picture.
We'll look at an approach. I'll go over an approach here where we can probably find the fiber.
Yeah, because it's the problem with the unification. How to define the fiber bundle structure?
Right. Where does it naturally arise from? You're right. Okay.
One idea is that at Planck scale, it's like there are these dualities. So the gravitational field could be defined in this structure that the unification field creates. So instead of look the fiber bundle in one point of space-time, you look space-time in one point of the unification E8 field.
Yes. So
what I'm thinking, though, guys, is that there is no time and that there is only space, and that the fiber bundles, the discretized fibers, they become transformed under projective geometry, and they become this phi field. And that phi field is all that there is. That is where your illusion of space-time emerges, and it's the behavior of the particles, as we've been discussing yesterday, which gives you a real notion of time, translation through time and space, but it's a completely different way of thinking than this idea of a four-dimensional smooth space-time as your base. So in other words, what I'm saying is I think that the base is the transformed network of the fibers. And you can chase, and if you can microscopically see those fibers at the Planck scale, you could unfold them in a folding matrix, and you could reverse back up to understand what their pre-transformed structure was in the hyper lattice.
So what you're referring to here.
Yeah, in this regime is one unique structure that you can look from the 2 point.
Yeah. Okay, so what Klee was referring to is taking the E8 roots and directly splitting them up, which we can do, into the H4 and another H4. Right? So this is the quasi-crystal approach here. There's another way to break things down, which is more suggestive of the physics. So this kind of hides some of the physics, but we can also approach it from the back end, and that will reveal some deeper structures. So we can go down from E8, so we can break down to E6, and then we can go to an SO10. This is more of a grand unified theory approach, but grand unification, you saw, had issues with proton decay. However, those models, as far as I know, did not take into account non-commutative geometry, which would change the picture, right? Because the notion of non-commutative geometry take seriously the operator algebras that we'd find in quantum mechanics as fundamental.
Which use C-star algebras?
Yes. So as you see, most of the models of non-commutative geometry make use of C-star algebras, which is the formal way to look at algebras of operators in quantum mechanics, different quantum mechanical theories, right? So they can be infinite dimensional, we can have finite dimensional ones. But here we have exceptional structures, so there should be a corresponding exceptional C-star algebra for our purposes, and there ends up being one. And it's a C-star algebra defined over the 27.
Mike, I don't. If it's complicated, then say you can tell us at another time. If it's something you can give us a conceptual analogy or a breakdown, I've been dying to understand exactly why Elaine Kohns, right, the father of non-commutative geometry, says that the Penrose tiling, which you can just generalize to fundamental quasi-crystals, are the quintessential example of non-commutative geometry. Why? How? I don't understand.
I would have to look at his book again. He has a different view than I do. Okay. I took a different view because you've brought quasi-crystals to my attention. Yeah. So the way I'm seeing it now is projections from higher dimensions, as Dugan explained. And in his talk, from 5 dimensions, you could go down to the Penrose tiling. So it seems the magic is really occurring in 5 dimensions, right? It's 5. So I'm taking the 5-dimensional view on it, which might be different than Elaine Kohn.
Yeah, because I would love for somebody sometime soon to, like in the first 90 days here of this year, to try to understand the essence of why a quasi-crystal is the quintessential, which means the ideal example of non-commutative geometry. Like deeply why? Like why does, why? Because we know that if we can use C-star algebra formalism, we have a more plausible chance of quantum mechanically realistic physics. Right. And we know Elaine Kohns it must be correct when he says that quasi-crystals are really expressing non-commutative geometry.
In my blurry understanding, I think he explained like a quasi-crystal, it's like all are connected. None of the elements are like separate from others. It's like it's like the holographic principle or hologram. I mean, so he explained a little bit like that. I don't know. I mean, I don't know how to.
Yeah, I would look at it a different way, I guess, than he has. I tend to focus on the notion of pure states here. Which would come up in quantum mechanics. So the pure states should be related to these quasi-crystals here. I would relate the pure states here, which can be done with the roots. There are some states in the 27 that we mentioned earlier that behave as pure states. And I think that's probably the better way to view the quasi-crystals. And I'll take a look at that. Maybe I'll talk about it later.
Because that's the big question for us as we move forward is what is the ideal geometry of a quasi-crystal, whether it's the QSN or the Penrose tiling? What is this implied most natural geometry, I meant to say algebra, right? What is the natural algebra of a quasi-crystal? What are its behaviors? What's the formalism? And it shouldn't be some invented or non-discovered algebra. There's got to be, and Elaine Kohns thinks it's C-star algebras and non-commutative geometry. Right. So it seems like it's an important thing for us to understand.
Yeah, and so one example of a non-commutative geometry, you can think of a 3-point space and functions over this space. Right, so it's a very simple system. That can be described by, for example, 3x3 matrices over the complex numbers, if we wish. This is one way to define some algebra functions over these. So you can say, oh, well, Okay, so you have an algebra of 3 by 3 matrices over the complex numbers. And that is an algebra of functions that's non-commutative because these matrices don't commute in general. So it's a non-commutative algebra of functions.
Is it a tensor network?
These are tensors, sure. You can make, if you have a bunch of collections of these, right? So you say, okay, so I have these, and what if I attach some other 3 points, right? Yeah. And it has its own little
So you relate
algebra
each
functions.
matrix in a tensor
So
network.
yeah, you can see how we're getting very close to this. So if we arrange them aperiodically, then we can, you can see how we can use matrices to create a quasi-crystal. Yeah, so you can see it's not a big leap to go from collections of these objects. So I'm just looking at it locally. See, so if you look at don't look at the whole quasi-crystal, because the QSN, for instance, right? Can't we just focus on 1/600 cell?
Or 20 group, right?
Or even a 20
which
group,
is 5 cuboctahedra.
Mm-hmm. So within the mapping here for the hope vibration, it's taken us from a gossip polytope to this arrangement, this grouping of 24 cells, from which we acquire 2 600 cells. So this is just one local part there. So it's picking one point in the E8 lattice in which we get its nearest neighbors, which is the collection of 24, our 240 root vectors. And we can do that at any point, right? And we can acquire the network by repeating that procedure everywhere. So what's the difference here, right? You can see that we could be doing the same thing. We do it locally, and when we do that, we acquire some finite point space with functions defined over it that are given by these matrices. And if we relate different patches to each other, then we can slowly build up a space from a network. Right. And that's eventually where we want to go. But we're very close. We're very close to connecting this quasi-crystal approach to non-commutative geometry. And the question is, what are the right matrices? Right? And that's where we're getting to. I think we have a really good guess at this point, and it involves an exceptional C-star algebra. Yeah, there's a certain one that we'd probably use. Cool. So, okay, so that's kind of an overview.
So you're going to have to eventually teach everybody here C-star algebra.
Yeah, it's a certain. We have the star. You can think of it as a sort of conjugation that we have over the algebra, and the C. Usually these are defined over the complex field. So it's already, a lot of it's encoded in the name itself, and the rest are just properties of, you can define a norm within the algebra and it satisfies certain properties. So that would be a different talk. Okay, so let's look inside this breaking here. So, you know this as the D5.
D5, I was just going to ask you that.
Yeah,
Okay.
the D5.
So SO8 is D4 and SO10 is D5.
Yeah, so it's the D5. So you can see, I mean, D5 is one of the usual suspects. Another way is to go from E8 to E7 to SO12, which is the D6. And you've seen Ray. Yeah. Ray has his own way of approaching the QSN through D6. Uh-huh. So there's different roads, but they should all lead to Rome.
You're Rome, yeah.
Okay, so I'll go ahead and let's look a little bit at an approach related to Cole-Fiery's approach at acquiring the standard model. So we have a notion of octonionic units, and we can look at the octonions complexified. So we can look at complex numbers whose coefficients are octonions. Okay, so we're not going to get deep into this, but I'll just write them out. So a complex number would be something of this form, right? But imagine now that the A and B are octonions. So in other words, I'll stick one of the E's in there and another E here. But I'm going to do it in a very precise sense. So let's take a basis for this, the complex octonions. And we'll take U1 as 1/2, E1 plus I, E4. So I'm doing it because I'm doing it this way. This is, as you see, this is 3 more than that. So when you choose them, so it's 3 more, you're in a quaternionic subalgebra. So this is just one way to look at quaternionic subalgebras here. So we have the E2, so E5 and the E3. And let's have the U not here, which is a little different from the bunch. That makes use of E7. So you can see 1, 2, 3, 4, 5, 6, 7. So we're using all of them. But the difference here, you see, is this has 1. So this is not using one of the imaginary units. So this guy is a little different from the bunch, which will play a role here. So now if we, instead of using this notation where we write them as complex variables, let's go ahead and put them in a column instead so we can actually start working with them. Okay, so this is just going to elucidate some of the properties that we see with the standard model. Okay, so this is just one approach here. So now you can think U0. Oh yeah, mapping here. So we map it to a column. So we have one component there. That's an octonion component, another one here. So these will be, you can look at it as column vectors that are elements of O2, which is just an O cross O. Okay, so then we have the U1 here, which we have E1, E4. Okay, U2. So I'm just dropping the 1/2 for now. I'm just trying to make it look easier. E2, E5. And then we have finally the E3, E6. Okay, so now we have columns. So naturally, we can transform these with a 2x2 matrix because this is a 2-component column. So this is nicer. It makes it a little more clear than this notation here. So these are, you could think of this as some isomorphism in some sense, right? Where we have the complex. And they do that with complex numbers as well. Sometimes you write them as a 2-component column. Okay, so now this space here will be acted on in general by matrices. You could think that are in this group here, special linear 2x2 over octonion. Okay, so these are invertible matrices that have determinant 1. Okay, so this, you could think of this as if this is a space of an octonionic 2 space, these are affine transformations. So this is very much projective geometry that we're, so if we look at the full set of affine transformations, it'll be of this form. And this will be pretty much, it's roughly equivalent to rotations in 9,1 signature. So this is 10-dimensional, where 9 are behaving like space and 1's time. So they look like Lorentz transformations in 10 dimensions. So it's pretty nice. You have this correspondence here. Now, what would a matrix acting on these look like? So we can write it as M. So I didn't have to invent it. Tevian Dre and Corinne Montague, they actually gave a certain matrix formulation for it. So I don't have to reinvent the wheel here. So they've did some good work. And we'll just use that just for these purposes. So they have a matrix of this form, Q and Q bar, and then zeros on the off diagonal. Okay, where Q is E raised to one of these units, 1 through 7. I'll just write it as S. Okay, so because it can be any of these times an angle. So it's like some polar form. Okay, and
Is the S a subscript?
well, the S is just going to represent one of these. I just didn't want to write E to the E.
Oh, and E is the
Yeah.
Euler's number.
Yeah.
Okay.
So it's in their paper too. I didn't run it. Yeah. It just looks funny. E to the E7 theta. It just looks like I'm doing a double exponential. But so I'm just where S is an imaginary unit. Okay. So say we give a specific value to this S. Say we pick one of the units, right? For instance, let's choose the E7, right? So we have, let's say it's the E7 here. I'll go ahead. Let's see. I'll just write it as I subscript 7. We'll just know that that's corresponding to that guy here. Okay. So it's doing some kind of rotation there, right? Now, if this matrix, which is an SO8 transformation, so now we see D4 coming up here. So this will be a rotation here. So it's some, you could think some D4 object that's going to be transforming these. If this acts on this object right here, it'll just hit it by phase. It'll just be like a phase transformation. But if it hits any of these, we're going to have to go back to the octonionic multiplication table to figure out what just happened. Okay. So, for instance, this you can think of as cosine plus I7 sine. If you really expand it, it'll look that way. Okay. Just polar form. So it's like we're using this polar form, well known in complex variable theory, where we're substituting this imaginary unit for any of the 7.
E7.
What?
I7.
Yeah, I just wrote I7 just so we won't get confused. So it won't be E to the E. Okay. So now if we say we choose another one, so this is just M1. So we have M2, for instance, now. So you can see this is hitting this by phase, which we would see as a certain type of vector boson acting on a state here, right? So that matrix will behave differently transforming this object than these, okay? So it's actually, it's seen them as distinct families, okay? And so I'll just write another example up here. So if we have E, say we have I4 theta. Okay. So for example, let's say the E to the I4 is hitting one of these, right? So we have to go back to the table and figure out what just occurred with the phonoplane. Okay, so here we go. So if we think that it hits within, let's say 1, 4, for instance, corresponds to 2, okay? So the 4 and the 1, okay, so which over here, let's go back to our good notation. So the E1 or the E4, right? The E4 hitting the E1 is giving us the E2. Okay. So if the 4 hits the 1, it's going to take us into an E2, which is a quaternionic subalgebra. Now, the symmetry of this quaternionic subalgebra is of the type SU2. So it's very nice. So it's very suggestive, you would say. Okay. So we have an SU2 there. So this SO8 is actually breaking. You can think of it as it's, depending on the state it's acting on, will break to a smaller symmetry within the SO8. Okay. So as you see, the full symmetry is this, however. That's actually the full symmetry. So
Do you know how to decompose SL2O in SL2C?
To break it up? Yeah, you're right. Yeah. So the SL2C, so we can actually decompose this. Okay, we can look at if we Marcelo had noted, if we consider SL2C, right, then that actually gives us the Lorentz group, which is nice because eventually we want something that looks like the Lorentz group if we're going to be doing special relativity, right? So this is very nice here. But whether we can actually capture it here if we break this, the SO91, in a certain sense. So let's think about it. If the SO8 is acting on 8 directions, right? 1, 2, 3, 4, 5, 6, 7, 8. But if we choose one of the units, and it's only hitting these by phase and it's doing something non-trivial on these, then we've just identified 1, 2, 3, 4, 5, 6 directions in which they're special, okay? Because they're not being hit by a phase. And those, so we've reduced the SO8 to an SO6. And the SO6 we also know is equivalent to an SU4, which in the QSN we see as roots that give you the cuboctahedron.
So this corresponds to D3 and A3.
Yes, D3 and A3, yep. So we see this all the time. Cuboctahedron is a usual suspect within the QSN. So what this construction is saying is to focus on the cuboctahedron because it's telling you something about these states. Right. Now, what kind of states are these? Well, through Cole's analysis, Cole has a whole PhD thesis on these states, which she represented in this form. Right. And she identified these states with quark states. Right. And this state is a leptonic state.
And so this 5 cuboctahedra forming the 20 group, which if there's any root vector polytope in a quasi-periodic structure, which that's not a proper term, but something analogous to a root vector polytope would be the 5 compound of the cuboctahedron 5 compound, which is the 20 group.
Yeah, so it's not too mysterious because remember, the SO8 gives you the 24 cell. So essentially what we're asking is, if you're curious about the QSN, okay? And so the analogous, this breaking here is analogous to looking for, so where is the cuboctahedron, or I would say a cuboctahedron, but in the 24 cell. That's all we need. That's all this is saying. It's saying there's a cuboctahedron in the 24 cell. Somewhere.
Right. Right.
And this would be the corresponding physics for it.
Right.
So it's saying if you have a 24 cell and you can identify a cuboctahedron, then it'll give you something equivalent to Cole's quark states.
How many cuboctahedra would it take to construct a 24 cell? Does anybody know?
Have you guys?
How many cuboctahedra would it take to construct a 24 cell?
In fact, when you project into 3 dimension, you get the cuboctahedron.
Yeah, I don't know if it's a compound. It can be a compound.
Not a compound.
Yeah.
But you you may be able to construct. For example, you can construct it from octahedra and tetrahedra, the 24 cell.
Yeah, but it's like how many hexagon you use to compound to construct the cuboctahedron. You know, one's a 2-dimensional thing, the other one is a 3D. And here
But there is a number. There's an answer to that question. We solved that once. How many hexagons would you need to construct one cuboctahedron? So I wonder if you, first of all, can you construct a 24 cell with some quantity of cuboctahedra? And then if you can.
Some compound, you're saying, right?
Not a compound in the ordinary sense, where you
the
normally think
intersection
and all
or
that.
maybe.
Well, normally when you say compound, you're imagining things being rotated upon a centroid, copies, normally, but in another way you can say, well, I can construct a cube with 6 squares.
Right.
And I can certainly construct a 24 cell with some quantity of tetrahedra, where there are interstitial gaps or octahedra. But wherever you have octahedra and tetrahedra, you sometimes have cuboctahedra.
I think at the 24 cell, if you slice it through the middle, you probably get a cuboctahedron.
Okay.
You take a central plane.
Okay. Right. That would be worth investigating. So, of course, this can be lifted to the 57 group as well. So we can study tetrahelices and also relate them back to these structures. So this would be where the physics would lie. So it's you see the 24 cell playing a very prominent role, but it's slicing of the 24 cell that's actually giving us some particle structure there. Okay, so we've seen this larger symmetry here, which contains an SO8, okay? So this larger one, we know this SO10 is actually in an E6. So now we go back to the picture that we began with, right? So we'll go back there later, but for right now, what Marcelo asked is to identify an SL2C within here, okay? So if this SL2O is equivalent to this, then what would be the natural way to identify an SO31 in here? Okay, well, the most naive way to see it is we identify the SO6, which we did over here. Okay, so we said, okay, I got an SO6 here. So it's possible to break this up. We take 6 directions away from space, and it's not, we have extra dimensions left over, obviously. But we can split this SO91 into an SO6 and an SO31.
Which is an SO4.
Which is, we know this as the Lorentz group of transformations, okay? So, as you recall, we had the E6 here, and it's actually a very precise E6. Okay, so within E8. So the version, the non-compact version, so it's a real form of E8 that Garrett was actually using, and it's called E8 minus 24. So this is the non-compact generators. It has generators for the algebra, and these are counting the non-compact form. So in here, this is a certain version of E6 that is contained in here, and that's the E6 minus 26. Okay, so this is actually going to be acting as the affine symmetry group of that space OP2. Okay, so I'm going to represent OP2 as a 3-point space. So we're going to go back to the non-commutative geometry and the perspective of finite point spaces with interesting algebras of functions over it. Okay, So you can think of OP2, we can represent it as a type of 3-point space in the sense that it's coming from 3 by 3 matrices in this algebra, the exceptional Jordan algebra. And within this algebra, we can define orthogonal pure states, which in the nice basis, you could say in the diagonal basis, they look like this. So you just see the 1 on the diagonal here. And these are orthogonal in the sense of matrix. You can have a matrix orthogonality. Okay,
So
that's defined.
These numbers, I'm sorry, these numbers are all octonions?
The off diagonals are supposed to be octonions, and the diagonals are supposed to be real. So this is the standard basis, but if we start rotating out into these octonionic directions, things get messy. But when we have it this way, it's very nice. So we can actually, you can think of the transition between a type of fuzzy matrix geometry, and then we go to classical, which is what we expect. So if you return back to the mathematics that general relativity is based on, it's Riemannian geometry. So Riemannian geometry was created by Riemann in the 1800s, the late 1800s, where there was no notion of quantum mechanical operators, right? That came up after Riemann's passing. And it was emerging at the same time that Einstein was studying the photoelectric effect, special relativity. He didn't embrace it fully, but if he would have embraced it fully, he would have discovered non-commutative geometry. And that's where we seem to be at this point, especially with the quasi-crystals. So what happened in 1934 was that this algebra was actually classified in a paper by von Neumann, Wigner, and Jordan, Pascal Jordan. And so there's many people don't know the history of Pascal Jordan because he was a little overshadowed because he did not leave Nazi Germany during World War II. So he's a little, he's one of the fathers.
He didn't get to
quantum field
participate in
theory.
academia for those years, right?
He did, but he just wasn't, I would say, like politically acknowledged in the community because many of the scientists had exited Germany at that time. But he is one of the fathers of quantum field theory. And this is one of the algebras that they found when they were classifying the possible finite dimensional operator algebras for quantum mechanics. So they had this classification, and this was the oddball, which is known as the exceptional Jordan algebra. So if we have a quantum mechanics corresponding to this strange operator algebra, and this would be an algebra of observables because they're not just any matrices, they're actually self-adjoint. So if you take the transpose and you take the conjugate of everything inside, it gives you the original matrix back. So they're very special, and these are enjoyed by physicists because they have row eigenvalues. So we can return eigenvalues, right? So row eigenvalues is a nice property because when we're making measurements, we want real numbers, not complex numbers. So that's where we pick this subset of self-adjoint operators, which is contained in a C-star algebra. So the C-star algebra is more general. It has more general algebraic elements than these self-adjoint operators. But when you're doing quantum mechanics, practically, you want to work, you're usually working within a Jordan algebra. Let's just put it that way. Okay, so this OP2, we can represent it as a 3-point space, and we can look at algebras, an algebra of functions over it, which happens to just be the Jordan algebra, right? So in the process of transforming this plane, okay, so it's some very abstract plane, it's 16-dimensional, but for illustrative purposes, this will be okay, 3-point space. So we can transform it. Its largest symmetry is the E6, 26. That's the affine symmetry of this plane. And it's the group of transformations of the Jordan algebra that preserve the determinant. So the determinant is sort of like if you think of it geometrically, it's like a volume preserving transformation. So E6, let's say we're acting on the plane. Every general transformation that we can perform, we can reduce it down to smaller transformations in which we fix a point. Okay, so fixing a point here breaks this symmetry to a smaller symmetry, which happens to be, lo and behold, SO91. So that's where the SO91 comes from. It's actually coming from the center here. So if this is the E6, the way it's transforming these nodes here, collections of vectors, right? If I close these up, it'll just be some 27-dimensional node. The way it's transforming those is by fixing one of these points and transforming the other two. And each time it fixes a point, it's breaking to a different SO91 within itself.
In what sense does it transform the other two?
It rotates them. It rotates them in these octonionic directions.
Okay.
Yeah.
So is the representation again in projective geometry?
Mm-hmm. This is projective geometry. Yes. It's just a very weird one. I would call it exceptional projective geometry.
So Mike, in other words, the 3 points themselves live pre-projected, right? Pre-transformed, the 3 points living in this higher dimensional space themselves live on a 2-dimensional subspace because they're 3 points. So
they're 3 points?
Yeah, so they would logically live on a plane. But then just as you can rotate a triangle in 3 space, an equilateral triangle in 3 space to produce any possible triangle that sums to 180 degrees, right?
Yeah.
Similarly, you can do a lot more rotations in more directions in some sense if you rotate a 2 simplex in this higher dimensional space, and the set of the various triangles that are transformed in some n minus m dimension, wherever your projective space is what you're talking about here, these operations.
You're perfectly right. And I'll draw the picture for that. So this is the more abstract view of it. But let me take a matrix from here. Okay. So when you find the eigenvalues, you can write it in terms of those eigenvalues. And those eigenvalues will be some coefficients. So that's called the spectral decomposition of some matrix. Okay. So we have eigenvalue 1. P1, so P1 is going to be a rotated form of one of these. And then we have eigenvalue 2 and P2, which will be another rotated version of one of these. And then we have the third eigenvalue and its corresponding projection operator, which are the pure states. So as you see here, this is very much like a 3-dimensional geometry. So if we have an axis that's given by the P1, it's almost as if we don't look inside the P's, they're just the basis elements. They're hiding a lot of information that's octonionic and strange. But if we purely look at it in terms of the spectral decomposition, P1 is just a direction. So we have P1, P2, P3, it's 3D. Yeah. So we took this wild 27-dimensional object, but once we find the eigenvalues, it projects to a 3D. Right. And so we can represent that as a simplex. You're right. And it'll be this form.
A 2 simplex, though.
Yep, 2 simplex. Yep. Yep. That would be the corresponding 2 simplex for this operator.
But it wouldn't be regular as this, meaning these so it's as though you can have one way to say it is, let's say you restrict yourself to a set of up to one possible triangle. Let's call it a golden triangle, just to use an example.
Right.
Like related to like the idea of H3 and H4, where you want to stay in those symmetries. But to get to that golden triangle,
Yes.
you can choose several identical angles where the angles themselves are just playing off different angles in your hyperspace.
Yeah, so this is just very general, but if we're working let's say if we have our quasi-crystallization occurring. So one nice thing is that these p's here, they actually come from root vectors. It's actually these guys that take directions along these inner roots. So they're almost following them. Now, these here are what Garrett playfully referred to as 1/3 gravitons. But in a certain sense, it's almost as if they're related to the Higgs mechanism as well.
Wait, so he calls
These X bosons, he just playfully referred to them as 1/3 gravitons because they're in a certain sense, they behave like, together as one, they behave like a
and what you're
graviton.
saying is those relate to your projection, those are your restrictions that
Yes.
relate to the restrictions there.
Yes.
And you drew 3 matrices there.
Mhm.
So it's kind of cool because you could orient this golden triangle that I'm using as an analogy in three different ways. And each orientation of the same triangle was by a rotation of the same basic hypervector, but with different discretizations relative to these nodes here in E8.
Yeah, so the full algebra was, okay, so what we're doing is we have these directions, these P1, P2, P3, which we can also look at as probing a 3-component object. That's 8 plus 8 plus 8, 24D. Okay, so it's almost as if these eigenvalues are corresponding to these guys choosing 3 directions. So 3 of these, it's like 24. 24, choose 3 or something, right? You can roughly think about it. It's choosing these 3.
This is where you get your notion of 3 directions of time.
It could be related to time. It could be related to also mass generation, because that's usually what happens when you're finding the eigenvalues. It's going from fuzzy, non-commutative space to classical, because you got rid of all the fuzziness because it's all contained within these.
You restrict it.
Yeah, because you chose some preferred directions for this operator.
Right.
So that's the transition. So you can think within the QSN, that's going to be occurring as well, because these are the same root vectors.
Right.
So this is already occurring in the QSN somewhere.
Yes, you're restricting yourself, but in a very non-arbitrary way, which is really what I mean when I talk about the AB equals P operators, where you restrict yourself to this angle, this non-trivial hypervector angle that you pluck out of a 4-dimensional subspace of E8.
So you can think, okay, if you're only allowed certain distances that are written in terms of the golden ratio, then that would restrict these eigenvalues. And if these are related to the masses of some particles, then your masses should occur. You rotate to a frame that is parametrized, or that has some memory of the golden ratio, and your masses should be
right. But it
not just arbitrary.
Yeah. But on the face of it, it doesn't look like a golden ratio value.
No.
The non-trivial hypervector in A is actually just arc cosine 1/4. It's just that when you cast out the arc cosine 1/2 component of that angle, you get 3 phi minus 1 divided by 4, the arc cosine of that.
Yeah.
So it's like embedded in there.
Yeah, and just as Ray has shown, you can rotate the E8 Cartan matrix in 9 dimensions and diagonalize them, and then you already see the golden ratio appearing. So we're calling that a golden basis for E8. So if you work within the golden basis, then it's probably pretty natural to see this. If you write this in that golden basis, then sure, there should be some kind of appearance of the golden ratio somewhere within these certain angles, and that means that the masses, if this is applied to the standard model, that the masses would not just be random.
Right.
They would actually be of a certain form with
Right.
respect to that golden basis. Yeah.
Good.
Cool. Yeah. So we can stop there.
Yeah, this is excellent, Mike. We got to do more of these talks. This is wonderfully instructive.